Hello everyone, welcome to topic 7.2, direction of reversible reactions. By the end of this, you should be able to explain the relationship between the direction in which a reversible reaction proceeds and the relative rates of the forward and reverse reaction. So in a reversible chemical reaction, the reaction reached equilibrium when the rate of the forward and reverse reactions are equal. Okay. When the rate of the forward reaction, which is left to right, is greater than the reverse, the reaction is not at equilibrium and products are being made faster than the reactants, and therefore there's a net gain in the amount of products. Okay. The net gain in the amount of products will occur until a reaction reaches equilibrium. At equilibrium, the amounts of both reactants and products will remain constant because the rate of the forward and reverse reactions are equal. The same is true when the rate of the reverse reaction to the left is greater than the forward reaction. The reactants are made faster than the products, so there's a net gain. So if we are at equilibrium and we add reactant, we end up speeding up the reaction rate of the forward reaction. But it's only temporarily. It ends up decreasing back down once it reaches equilibrium. Until it's at equilibrium again. And vice versa, if you add products, so mirroring these, this time though the reverse reaction rate increases until equilibrium's reached again. So it like spikes and decreases again. So we're going to look at how this applies here. So the reaction N2 plus 3H2 yields 2NH3 is at equilibrium at 500 Kelvin. What happens to the rates of the forward and reverse reactions if we add a little bit of NH3 at time t? So at equilibrium, what happens if you add a little bit of NH3? Well, if this means that you increased the amount of NH3, and to do that, because it's a product, you have more products than reactants. So the reaction the reverse rate of reaction increases to reestablish that equilibrium. Okay. Now for our redo, in a previously evacuated 1 liter flask, 0.4 moles of A and 0.5 moles of B are added and allowed to come to equilibrium. At equilibrium, there's 1.5 moles of C. The equation for the reaction is given. Sketch the 3 curves below to show what happens as it reaches equilibrium. It doesn't tell you where it reaches equilibrium, so you can pick anywhere. But we do know we have to start at 0.4 for A 0.5 for B, and then C technically starts at 0. But we have a hint in that C should end up at 1.5 eventually. And I'm actually going to make this easy on myself and not worry about trying to make it happen. So then for the other two, we know that A has the same ratio as C, so whatever C increased is how much A decreased. So A is at 0.4, it should decrease by 1 point, or 0.15, so that means 0.2 here, so .25, I mean. So that should draw out there. And then B, so this is C and this is A. B then decreases twice as much because it's got this coefficient 2. So it should go from 0.5 to 2 here. So I have to sketch that. And that would be B. Okay, so our equilibrium is around here when they all become flat. And they should still mirror, as long as we're given some values, the stoichiometric ratio. Okay, that concludes the 7.2 notes. Please complete the you do, and thank you for tuning in.